Hello, everyone. Good afternoon. I would like to welcome to today's webinar, where we will be looking into the results and lessons learned on 5G for CAM from the 5G MOBIX Trial Site in France. My name is Sevi Christoforou. I am a Communication and Dissemination Officer with ICCS, the Institute of Communication Computer Systems in Athens, Greece, and I'm also the Dissemination Task Leader for the EU 5G MOBIX project. Today, I will be the moderator of the webinar. And before we start, before I move on to introducing the speakers of today and the agenda, I would like to inform you that throughout the webinar, you will have the opportunity to submit your questions to the speakers by submitting your question to the question box that you can see on your control panel. Sorry. And if you're experiencing any technical issues or you have any questions about any technicalities, please feel free to use the chat box that you can also find on your control panel to contact the organizers, and one of us will attend to you as soon as possible. Now I would like to introduce, to welcome our speakers and introduce them. So I will ask them to turn on their cameras so we can also see you. Our first speaker for today is Camille Plistan. She has studied European Project Manager, and she's currently a European Project Manager at VEDECOM. She's in charge of setting up collaborative projects on connected and automated vehicles at the national and European level. She has been co-leading the trial coordination of the EU project Autopilot, and she's also leading the 5G MOBIX trial coordination. Today, she will introduce us to the 5G MOBIX project and also the French trial site. Next, we have Laurent Fevrier. Laurent has 20 years of experience working for military communication systems and over 14 years of experience managing the NSE R&D Center in France, dedicated to 3G and 4G technologies. Since 2015, he's chief engineer at VEDECOM as well, involved in several national and EU research and development projects addressing communications and perception infrastructure for automated vehicles. Today, he will be describing the technical challenges and also the applied solutions derived from the 5G MOBIX trial site experience in France, and also sharing some lessons learned from the experience. Now, last but not least, we have with us Dr. Pierre Madrinak. Pierre has a Master of Engineering from Telecom Bretagne, and he's also a PhD holder. He has a PhD in robotics from Mainz Paris Tech. He has an extensive research experience working with leading research institutes in France, and currently in VEDECOM, his research work focuses on delegating driving and connectivity research axis, currently leading the connectivity activities. His research interests include cooperative ITS, communication technologies, multi-source information fusion, and context awareness. In this webinar, he will take us through the contribution of the French trial site and the activities of the French trial site to the cross-border corridor issues. It is our pleasure to have you here with us, and with that, without further ado, I would like to begin the presentations. Camille, I will make you the presenter, and the floor is all yours.
Okay, hello everyone. So I'm Camille Plistan. I work in VEDECOM. I'm involved in the French trial site, and also I'm the work package 4 leader of 5G MOBIX, which is the work package on trials. So I will start with an overview of the 5G MOBIX project, and then I will give you also an overview of the French trial site before my colleagues go into further details on our trial. So 5G MOBIX is a EU-funded innovation action project from the Horizon 2020 program. It started in November 2018 and will end by September 2022. This project gathered almost 60 partners from 11 different countries in Europe and also 9 partners from China and South Korea. The objectives of 5G MOBIX are, first of all, to accelerate the deployment of 5G at cross-border areas. So for that end, we've carried out trials along the cross-border corridors to assess the 5G capabilities for CAM. We also qualified the 5G infrastructure and evaluated the benefits of 5G within the CAM context. Also, we identified the spectrum allocation gaps and contributed to the standardization and the 5G CEF preparation. Also, an objective of this project was to define the deployment scenarios and recommendations, including in cross-border context, to perform cost-benefit analysis and impact assessments to identify new business opportunities for 5G-enabled CAM, and to investigate the legal, regulatory, and security issues. Concerning the 5G MOBIX trials, we have several locations in Europe and in Asia. The trials were located in 2 cross-border corridors, so one in the Spain-Portugal area, so in the corridor between the cities of Porto and Vigo. One in the Greece-Turkey cross-border corridor. We also have 4 complementary European trial sites. So the French trial site that we present today, the German trial site, the Finland trial site, and the Netherlands trial site. And also we have 2 complementary trial sites in Asia, one in China and one in South Korea. So concerning the network, we had 29 5G DNB network. We were working on NSA architecture. We were using 20 L4 automated vehicle and implementing 5 use case categories. So the advanced driving, the vehicle flattening, extended sensor, remote driving, and vehicle quality of service support. So within the project, we worked on the identification of and the categorization of cross-border issues of 5G for CAM. So within the project, we identified 11 cross-border issues, and with these issues, we've also identified solutions that we could apply to solve them. And we've identified actually 26 solutions. Within each trial site and cross-border corridors, we've addressed these issues and solutions and worked on different solutions, so locally and at the border. So on this slide, you can see an overview on of the cross-border issues and all the solutions that we've addressed. So my colleagues Laurent and Pierre will specifically address the one that the French trial site tested and implemented. So concerning the French trial site, so we at VEDECOM worked with different partners from the consortium. So in VEDECOM, we are the trial site leader, the site and test site provider. We also provided the application, make the OBUs, the vehicles, the roadside sensors. And we also led the different testing and trialing sessions. Catapult provided everything related to the satellite communication solution. ACA provided the MEC, and Valeo provided the OBU. In terms of the operators, we used different NSA commercial and experimental networks, so the one of Bouygues, Orange, and TDF. We performed tests and trials in different type of road and location, so on close tracks in Satori and in the Tecmo, but also on operands in the Yvelines department and also in a cross-border corridor in Spain, Portugal. The French trial site implemented different test cases. So the main use case that we were implementing is the infrastructure assistance advanced driving. We also implemented the multi-SIM and satellite communication and the quality of service prediction. And finally, concerning the trials, we started our pre-testing back in September 2020, and our final trial sessions were done in early June 2022. And we also went at the cross-border corridor in Spain, Portugal in March 2022 to implement our contribution. So speaking about the French trial site contribution, so briefly just to give you an overview. So in 5G MOBIX, each local site define and develop a contribution that it could transfer to one of the both cross-border corridors of the project. So in the case of the French trial site, we transfer the connected vehicle to the Spain-Portugal cross-border corridor. This French vehicle was equipped with a double-stack OBU and a safety mechanism that we developed. And the objective of this contribution was to test the interoperability between the French vehicle and the 5G and the infrastructure at the Spain-Portugal corridor, and to test the multi-SIM solution where the French vehicle can connect to the Make in Spain, the Make in Portugal, by using a multi-SIM in the overlapping coverage area. So that's it for the brief overview. We would like to show you a video that we've produced for the French trial site that will give you some more explanation on the use case that was implemented here. So Julie or Céline, if you can show the video, please.
Yes, 1 second. Thank you, Camille.
Thank you.
1 second.
Le projet 5G MOBIX a pour but d'évaluer l'apport de la 5G sur les services de mobilité connectée et automatisée dans des conditions transfrontalières. VEDECOM a coordonné le site français et évalué les cas d'usage de conduite coopérative assistée par l'infrastructure 5G et la connectivité simultanée sur des réseaux multiples. Avec nos partenaires, nous avons développé et déployé des unités embarquées de véhicules, des capteurs de l'infrastructure, un réseau 5G et des applications pour les véhicules et des infrastructures. Nous avons ensuite exécuté des tests pendant plusieurs mois sur des sites français ainsi que sur route ouverte en France et sur la frontière entre l'Espagne et le Portugal. Les résultats des tests ont été analysés et le test montre les pertinences des solutions déployées.
La 5G apporte 3 nouveautés. L'ultra haut débit mobile, les communications fiables et à faible latence et aussi le Massive IoT. Dans le cadre de ce projet, TDF a apporté une infrastructure 5G complète avec d'un côté un cœur de réseau, un réseau de backhaul, un réseau d'accès mobile et aussi une solution de mobile edge computing pour réduire la latence entre les communications mais aussi augmenter la fiabilité. Ce projet nous a vraiment permis de comprendre l'importance des partenariats entre le monde du réseau dont nous venons et le monde industriel et de la recherche avec des instituts comme VEDECOM.
Many thanks to the whole team for this video. And now we will move on to the second speaker, Loren, who will be describing the technical challenges and applied solutions. Loren, give me 1 second.
Okay. Everybody see my screen? Okay, so the second part is presenting the technical challenge of the 5G MOBIX French Trial Site. So as you see in the video, we perform 2 use cases to demonstrate the capabilities and to put in place the considered solution addressing the cross-border issue in the French side. So one is guidance from the MEC given to the automated vehicles thanks to the analysis in the MEC of the risk analysis of collision avoidance. And the second one is the cloud and MEC assisted lane change thanks to contextual speed adaptation at the change of domain. So as Camille presented, we perform in French trial site 24 test cases addressing 6 over the 11 cross-border issues and in implementing 9 of the considered solutions. So mainly we have been involved in cross-border issue 1 with 1 test case, in 4 with 3 test cases. Major one was cross-border issue 5 with session and service continuity with 10 test cases. We also been involved in XBI 8 with a dynamic queue test case. The XBI 9, which was using the PC5, was planned but done because lack of chipset. And also an important part of VEDECOM work was to study the millimeter wave applicability, for which we implemented 7 test cases. So looking at the technical challenge we have to address in the French site, first of all, the development of a 5G OBU was to be performed. So we need to develop an hardware with a compact unit with several radios, and we face some lack of availability of 5G chipset at the time, especially for 5G millimeter wave and PC5. And we have also to develop the software with a V2X application client dealing with map, CAM, CPM, and MCM messages, for which we implement early V2X client in the OBU. We have also to develop the V2X application server using the first design of the first specification of the V2X server as defined in 3GPP. And so we developed this V2X application in the mobile edge computing with communication and using this primary architecture of V2X application server. We perform early experimentation of 5G millimeters, and I will come back on that as it was not so easy. And so for that, we have an experimental network which was deployed in Sateri, as we've seen in the video. And we also have a UE evaluation kit to make the test. Main performance, main test case and main challenge was the service continuity with multi-SIM and SATCOM solutions. And we test the handover or continuity of service between 5G centimeter wave and 5G centimeter wave, 5G centimeter wave and 5G millimeter wave, and also 5G centimeter wave and SATCOM. And we do that with link aggregation and without link aggregation to check the difference. And last but not least, the QH prediction was also to be implemented. So in terms of solutions which were in place, so as we saw previously with Camille, we have 3 5G networks. One TDF network, which is an experimental private network with one G.B in Sateri, using the band N258 on 26 GHz for the 5G millimeter wave. With Bouygues, we have 2 G.B, one in Sateri and one in Tecmo, using the 3.5 GHz band. And with Orange, we have also in Tecmo an experimental network with 1 G.B also. And you see on the right some photos of the different equipment of the antenna, the coverage of the 5G millimeter wave on bottom left. In terms of infrastructure, we also have the mobile edge computing with 2 cloud. We have 2 cloud servers, one in VEDECOM and one in Catapult in UK. We have 2 MEC, one from TDF and one from ACA. We have several roadside sensors in Sateri. We use 3 RGB camera and 1 LiDAR to evaluate the incoming of the cars and the risk of collisions. And we develop in VEDECOM some applications, so the V2X application server for the CAM, CPM, MCM, and map message. We develop a module for perception data fusion, both for infra and automated vehicle sensors. We make the fusion object model of both perceptions. We perform a risk analysis and a trajectory guidance module, QoS prediction module, and the KPI managers to capture the KPI we have the result with. In terms of device, so we have vehicles themselves. So we have 1 automated vehicle level 4 from SAE with 5G OBU and satellite modem. We have 2 connected vehicles with 5G OBU. In terms of embedded device, we use for that 3 5G OBU developed by VEDECOM. And you can see here that this design of module using a SimCop 5G chipset based on Qualcomm reference design. And we also use 3 5G OBU from Valeo, all of them on 5G sub-6G band. And we use also 1 satellite terminal and intelligent router from Catapult, our partner. And in terms of software, from the device perspective, we have developed the protocol side, both IP and non-IP, even if you don't use the non-IP geo networking for V2X message, CAM, CPM, MCM, and map. We have this primary V2X client, even if not fully standardized as 3GPP, the quality of service prediction client and the KPI managers client. So the main challenge, and Pierre will elaborate on that after me, for the French site was to test the service continuity and service quality as key requirement for connected automated mobility applications. So the challenge were delay on roaming and handover, low radio coverage, and some sudden change in communication quality, for which the solutions we put in place are seamless handover thanks to multi-SIM solutions, or seamless continuity of service thanks to multi-SIM solutions, usage of satellite technology when we lose totally the coverage from cellular, and the QoS prediction. And on top of that, as per FR site contribution, we perform a study on 5G millimeter wave applicability to see if it makes sense to address that, to use that in automotive use case. And as Camille said, we also contribute to the cross-border Spain-Portugal when we bring a FR connected vehicle, a dual stack OBU, and some security mechanisms which were developed in French trial site. And we perform the interoperability test with both Portugal and Spain networks on communication, and also we perform the security interoperability. All of that during 1 week of test in March 2020 on the US ESPT border. And the multi-SIM solution was tested, which demonstrates created automated mobility service continuity in cross-border scenario. Thank you for that. And so now Pierre will elaborate on the details and the results.
Hello, everyone. Thank you for joining to this webinar today. So now it's my time to present you some of the results we have obtained during our tests. So the title of this presentation is about the contributions to the cross-border issues. So what we will do is okay. So what we will do is to go over the different test cases, the cross-border issues that were presented, some of the cross-border issues that we have addressed that were presented just before by my colleagues. What are the solutions that some solutions we have considered, and we have tried to group them into 3 different kind of test cases and scenarios. So first aspect are related to the roaming interruption, the NSA roaming interruption, the session and service continuity, and the low coverage area. So what the different solutions for this NSA roaming interruption consists in the handover using NSA networks. To test that, we have done some tests with our 5G OBU, especially in the network in the Spain-Portugal cross-border corridor. We have tested, as mentioned by Laurent, multi-modem and multi-modem, multi-SIM connectivity to address the session and service continuity. So we have done this with different type of technologies and network, and we also have used the satellite solution to cover for low coverage areas. Then in the second step, we will see what is the applicability of millimeter wave, so testing a millimeter wave 5G NSA network. This mainly has been addressed is using in our user story tests. So in our use case that was the infrastructure assisted advanced driving by using different networks, so 4G, 5G, sub-6 GHz, and 5G millimeter wave. And finally, the last part is about the dynamic quality of service continuity, where we have developed and demonstrated a predictive QoS solution, so to adapt the QoS to the performance changes due to roaming and handover. So first, let's start with the tests that were done on the multi-SIM connectivities. So the scenario that is tested is to have a multi-SIM 5G OBU that is installed on the car and to drive in the road, so that we will have a handover from one network to another network, so from one domain to another domain. So we have done this kind of tests in two different sites. First, we have tested in the French trial site between two with handover between 2 operators. so namely Orange and Bouygues with commercial 5G NSA networks. And also, these tests were done in the cross-border corridor between the Spain with Telefónica and the Portugal with NOS. So what we have to understand from these two configurations is that as we don't have roaming between different operators in the French trial site, we could only test this multi-SIM connectivity to as a first validation approach to see what are the performances here in good conditions, and then carry this contribution to the cross-border. So to detail what is the solution that we have used, we have one connected vehicle with an intelligent router that handles simultaneous connection with two 5G network. And this, as shown here, we have our OBU, we have one router, and it creates a VPN tunnel to one server. And so to maintain two connections with the 5G network, so that it can reduce the delay associated to the roaming and handover situations. And also, as in some cases we can aggregate multiple connections, it can increase the throughput. So we have this router that creates a tunnel to what is called a fusion module installed in a Make or cloud server that is in charge of receiving the data, reordering the packets so that they can be sent then to the applications, and this is transparent for the application as if the packet were directly sent from one single SIM OBU. And what we show in this second graph is the difference when we have two 5G networks. So we are attached with two different PLMN, 1 and 2. So we have the bandwidth aggregation here in the left side. And what happens when we have only one connection? We have some loss here. We see that the throughput can be down to 0, as if we have the simultaneous connection in the bottom figure here. We are able to keep the connection up. And we see here on that leftmost graph how, when we aggregate the flow from different networks, we are able to increase the throughput between different streams. So to go now more in the cross-border issues that we were addressing, we have done first some static tests in France, where the configuration was to have first one SIM that is connected to one network, so network 1. Then at the second time, we connect the second SIM to a second network, so the network 2. So packets now can be sent to both networks. And finally, we can disconnect the SIM at the last time, the SIM from the network 1. And what we see from our first experimentations is that if we consider the delay, we see that on average for UDP and TCP streams flows, we have between 20 to 45, 50 milliseconds of delay. And when we disconnect, we see that on the UDP flow, we have some penalty that is about 30 milliseconds. And in the TCP flow, we have penalty that can be about 150 milliseconds compared to the baseline delay. Also, we see when we connect to the second network and look at the packet loss on the UDP flow, we can see that we have some packet loss from 1 to 6% of penalty in the connection and in the disconnection. So the time we need to set up the link, and then when we lose the connection, we have some few loss as well when we disconnect. So these results are obtained when we have some device, when we have a configuration in the intelligent router where we have different we are listening on different interfaces, trying to check if both are up or and are active. So we see that when there is a sudden here, the test is that we have to disconnect manually. So this is quite, as we call it, a failover, a brute force, and this takes few time for the router to adjust and then to get back to the normal behavior. So just to illustrate what we do, we have here a small video where we see on the left side the transmitted video from a vehicle, and on the right side the received video by another router. And we see here what happens when we switch from one network to another network. So just slowly, yeah, we see that we have some loss, but still we can maintain the video stream active. So now, after doing this first trials, we have carried the solution into the cross-border corridor, where we have our connected vehicle, which is installed with the intelligent router that was presented, and interfaces with the two SIM cards, one from Telefonica and one from NOS. And so the test that we have done is that the connected vehicles sends UDP flow to a server at 10 megabit per second. And one important point is that during that test, the server here was installed in France. So it was, we cannot say that it was MEC server, it was more a cloud configuration. And what we observed from, and what was important as well in that configuration, is that we know that the experimental networks here in the cross-border was with low coverage. So compared to what we have done in our local site, where we could have a large overlap between the two networks, here we have lower overlap. So this the solution can that we test can have more impact. Yeah, we expect more impact. So what we have obtained here in the bottom picture, we depict the results obtained with a single SIM. So now when we try to do only handover between the two network in green, so we see that in that case we have median interruption time of the service that is about 5 seconds, and that can be up to 70 seconds in the worst cases. We have tested the intelligent router in passive mode, meaning that it's just listening on the different interfaces and try to see if they are active. So in that case, we see that the median in service interruption time is reduced to few seconds, so a couple of seconds, about 2 seconds, and the worst results was about 25 seconds of interruption time. And another configuration of this router is the aggregation mode, where actually it's additionally to listening to the two interfaces, it also monitors the quality of the transmission to decide whether one or the other link is better to send some packets. So in that case, we see that the median service interruption time is quite similar, a little bit lower, so it's still about 2 seconds, but we have we have few on the worst case was a little bit lower, that is about 12 to 13 seconds. So we see that this multi-SIM connectivity with the link aggregation, it provides the highest performance for service continuity. It can give good provide good results and ensure the continuity of the service, especially when we were in good network conditions, so what we obtained in our local sites. And here, as the coverage is a little bit, the overlap between both network is a little bit lower, we had some longer disconnection, even if some tests were very the interruption was very short. And also one last point that we also got from the test is that there is an important impact that is related to the location of the monitoring server. So as we presented, there is a VPN server that is used to monitor the link, and as we installed it in France, we see that the delay was a little bit high, like few hundreds of milliseconds, which is higher than what we have when we test with server installed locally. So this is some aspects to consider when using this type of solutions. Additionally, in that to cover from the issue that is about the low coverage, we tested the satellite technology. So as presented, we used the Iridium Certus Leo constellation with the Thales Iridium Certus 350 land mobile that is expected to send throughput up to 500 kilobit per second, and that has a worldwide coverage. So one thing was to be able to equip the vehicle with this device. As we see, we tested it with the multi-technology router. So we have one 5G onboard unit. We have the satellite terminal that is shown here with its antenna and the router. So we have tested how much packets we can send with that kind of solution. So it was we managed to reach few hundreds kilobits per second and with few hundreds milliseconds of delay. So we see that this solution, it's for now only used as a backup solution when there is not terrestrial 5G that is available, as it has higher latency and some packets loss have been experienced. But it can maintain the connectivity. It has been shown that it can maintain the connectivity when it's used with the multi-SIM modem, so that then when terrestrial network gets back, we can get access to the service. So we can maintain a reduced data exchange during when coverage is when 5G network is not available. Now, after doing this, we have experienced our use case to test the performances of the 5G and how, especially to show how the 5G can provide benefits to that use case, and show and study if the millimeter wave can be the 5G millimeter wave can be a solution to for the different advanced driving use cases. So we have designed one scenario of such for our use case which consists on having vehicles that are merging on a motorway. So we have one vehicle that is driving on the main road, and it sends the cooperative awareness message and collective perception message to one MEC that is installed in the infrastructure. And we have one vehicle that is on an insertion lane trying to merge in front of the connected and automated vehicle. So this vehicle is detected by infrastructure sensor that provide this information to the MEC, so that we have so that it can be all this data can be processed by our V2X applications installed in the MEC. So we have these applications here that consist of data fusion and risk assessment to detect if there are any potential conflict at the merging zone, and that will trigger some message to coordinate the maneuver, so the MCM, and provide some recommendation to the cooperative and the automated vehicle, and which is in our case here a lane change maneuver, as it was illustrated in the video. What are the main results that we have seen here is that if we study first on the different data that are exchanged between the vehicles, the roadside sensors, and the MEC, we see that if we consider the V2X messages, so the cooperative awareness message, the collective perception message, and the maneuver coordination message, they mostly consist in sending few thousands bytes per second, so which is even lower for CAM and MCM, so which is less than 100 bytes per second. Though the collective perception message is a little bit bigger because it sends the list of objects that are in the vicinity of the connected and automated vehicle, so it can be a little bit larger. Still, compared to the capacity of the network, it's a little bit low. And if we compare now to the data that can be obtained also with camera or lidar, we can now get to few megabits per second, which is a lot higher. So this can be interesting to get some. So this shows that when we will want to send directly raw data, then having technology with higher throughput can become important. Another aspect that we studied is the impact of the MEC, and especially how it impacted the processing delay. So we have seen that we have installed some of our applications in the MEC to monitor the driving area with the extended perception, the risk assessment, the maneuver coordination. So we have seen some, as we show, this first picture shows the results of our detection algorithm, where we have here in green the different the vehicles that are detected on the main road. So in our test it changes from 1 to 2 depending on the number of vehicles connected vehicles we used. And when there was a vehicle on the insertion lane, we could detect the risk of collision, here illustrated in red, and trigger the maneuver coordination. And we see that to do this processing coming from the reception of the data, CAM or CPM, to the transmission of CPM, it could take, in our case here, about 20-25 milliseconds, and up to few worst case was about 220 milliseconds. So we see that using the MEC capability, we expect to maintain low delay and to communicate with the vehicle. And finally, the last results that we have done were on the measurement of end-to-end latency between the different in different technologies. So we have done some tests initially with the 4G, where we have measured an average delay of 29 milliseconds with median value of 28, and we have also done this test in 5G with an average value of 12 milliseconds. So if we consider this figure, adding with the processing delay of the MEC, we see that on our test we are here about we can have about 50 milliseconds of end-to-end latency to give the feedback to the vehicle, and we expect also some new improvement to come now when we will have standalone slicing to ensure more quality of service and have dedicated slice for the URLLC, for example. And also one aspect is that with the millimeter wave, as we can have higher throughput, we can now also go to the transmission of raw data and also which can help in supporting the vehicle for this kind of intersections that can be complex, this kind of complex driving environments. And finally, the last part of the presentation of our results, which is about the QoS adaptation to the performances changes in roaming and Dover. So we have developed some predictive QoS module that is installed in our MEC, and that monitors the conditions for where the vehicle is driving, to indicate to the vehicle if they should adapt their behavior. So as illustrated here, we have one vehicle that is driving, and then from the mobile networks, there is some notifications that future uplink data, for example, should drop below 20 megabits per second. So the vehicle will take appropriate actions, for example, reducing the resolution of video that it's sending, this kind of decision. So to do this, we have developed one module that relies on the acquisition of data, the prediction of QoS, and the notification to the vehicle. So I will show you our work that is about. So we have to build this module. We have made an extensive acquisition of data in the area of Versailles, Paris, Guyancourt, using different modems, so our 5G OBUs, but also one 5G smartphone, and that provides different information such as the timestamps, the location, the speed, and different KPIs on the access network, and also on the applications that were running on top of this on these systems. Then we have analyzed the different metrics that were obtained to try to learn some model. So what we have seen from this study is that the QoS prediction, it cannot rely on a parametric model with a unique parameter, but it's very complex because we have different parameters that can impact the quality of service. So we have to prepare a model that combines different parameters, and that should be considered. So we have tested different approach for doing the learning. So we have done a supervised learning, and we have compared the different root mean square error scores, and it appears that the random forest provides the higher performance. That is for comparing the real throughput to the predictive one, but we still need some fine-tuning of the model. And finally, once we have the model, the last step is to notify to the user what is the QoS that he will benefit. So we have specified one message, that is the EQN message, to send the information to the vehicle. So where we explain what is the destination source port. So the payload, especially the payload of this message, contain an action ID, the action element, so what should be done, what are the value that should be applied, and for example, when to apply this action. So upon the reception of this kind of message, the vehicle can adapt its behavior, for example, changing the frequency of V2X message transmissions, changing the size of the payload, or changing the resolution of video transmission. And one last thing is that on our experimentation, we have see that the kind of information that we transmit are mainly related to V2X messages or video. That is the most challenging type of data, but still it requires a lot of adaptation to transmit these parameters. And just to conclude, some illustration of our tests, of our module. So we see that we monitor here, for example, the data rate. So we see in the bottom left figure the data rate that is available, and based on that data run, we will send some IQN commands, so to notify the vehicle how to adapt its the data rate and its transmission, and then it's applied on the transmission of information. So to conclude this overview, we have been through these three different parts where we have seen that the intelligent combination of multiple technologies can be used to ensure the service continuities for some vehicle applications. We have studied that the 5G millimeter wave and to show the potential to be used in dedicated areas to support V2X applications, even though we still are in early phase, and these are only early results that we have today, and we're continuing on that direction. And also we have shown that for the dynamic QoS continuity, that it's important to collect data at a high resolution with the geolocation, so then we can precisely adapt the different parameters to the radio environments and support reliable usage of the network. So I will leave the floor now to Laurent to provide the main lessons learned.
Thank you, Pierre. Thank you for this very interesting presentation, and I will try just to summarize the main result and the main lesson learned and conclude the webinar. So as we have seen with Pierre detailed results presentation, we can consider that there are some key 5G benefits for connected automated mobility. And the main one is end-to-end latency improvement for V2X with 5G new radio and with MEC. And there is still room for improvement with release 16 to come, 5G SA and URLLC. So clearly latency improvement is, from my perspective, the key first key benefits from 5G. We also have this adaptive QoS that is also very interesting and considered as a benefits also. The high throughput is not so important for V2X message. However, it will permit upload of raw data from automated vehicles. For instance, we can have cameras, flow, and NIDAS cloud points upload to the network and to have some fusion perform in the MEC. That is something promising that for the future, and it's only possible with 5G today. And competition in MEC, of course, with the P gateway close to the road, to the AV is important. What we have also as other benefits, even if it's not experimented clearly in the 5G trials, 5G MOBIX trials, but it is behind as an enabler. We have now a reference architecture for 5G cooperative connected automated mobility, and the TS 23.2.6 clearly defines the functional architecture for V2X service in 3GPP reference architecture. So clearly we have now the merge of HC ITS architecture with 3GPP architecture, and that is something that which make possible tomorrow the deployment of solutions both in applications side and both in UE side. So clarification of mechanisms both for unicast and on new interface and broadcast of a PC5 are now there. And the V2X application server architecture in MEC is also defined. Even there is no today existing implementation, there is all at least roads to develop something. We have also a clear roadmap which has been elaborated in 5G AA that gives us the trends of what capability will be possible in which release for free. And very important also, and we use that as a reference at the beginning of the project, the use case design patterns in the technical specification 22.86, which defines the 5 use case, and we use the advanced driving use case to deploy in 5G MOBIX French trial. Of course, there are some drawbacks and some remaining issues, and I saw two main ones. The first one is that the 5G technology is still at early stage, and maybe especially in France, but I believe in Europe also there are several countries that 5G technology is at early stage. Release 5 is just an intermediate step, and there are no Release 16 networks in place for the moment, at least commercial networks. We have some private networks with Release 16. Commercial networks in France will not move to Release 16 before 2023 or later. We don't have chipset for CV2X over 5G ready yet. There are some early samples in Qualcomm. We have some LT V2X chipset, but which is not the future. So we are waiting for CV2X chipset for really have the PC5 implemented. And as for today, the 5G SA 4 mm wave is not yet defined in 3GPP. So maybe tomorrow that will be done, but for the moment we cannot anticipate a 5G SA millimeter wave networks. That is the first drawback, the technology not mature. The other one is that the 5G is complete and especially a complex technology. In the past, I've moved from 2G to 3G, 3G for 4G, but 4G to 5G is a very big step, and efficient settings are very complicated to put in place, both at network side and UE side. And both the network vendors and the network operators say that, and also at UE side we have faced some troubles to put the settings correctly. And fine-tuning is needed between UE and network, and that could take several months to reach the performance that are known for 4G. First of all, the positioning of the antenna in the network and in the OBU, and that's especially with the 5G millimeter wave. A couple of change in the light of scene is critical. The design of cells is complicated also for 5G millimeter wave. Setting the good beamforming parameters, it's not so straightforward. It's not very straightforward, and also to have this virtualization of the P gateway clear near to the GRAN is not so easy also. And to conclude this webinar, I would say that the 5G AA and 3GPP have defined the foundations for 5G technology to be a relevant enabler for cooperative, connected, automated mobility. We have the design pattern for the use case, we have a functional architecture for the V2X services, and we have roadmaps of service deployment in regard with the release. And even if the technology is at the early stage and not so simple to be deployed, it's probably already, it will be very effective and efficient for next generation ITS communication, especially with low latency, high reliability, and effective and are essential for automotive. And we have key improvement to come soon with 5G SA, with PC5, and with UARLC. And the scenario deployed in 5G MOBIX French Site trials demonstrate this effectiveness for low latency, high throughput, high reliability, and efficient adaptive quality of service. Thank you very much, and I think we may have some questions to come.
Thank you, Laurent. One second. Thank you so much, everyone, for the insightful presentations. Indeed, now we will dedicate some time for some questions. For everyone attending, feel free to submit your questions at the question box that you can see on the control panel. For now, I don't see any questions coming in. But as we wait, perhaps I could ask a question. I know, Laurent, you were very insightful in your presentation about the lessons learned and drawbacks. But overall, as an experience, what would you say, you or Camille or Pierre, what have been the major issues that you encountered when using 5G technology for COM in this specific trial site, and how did you tackle them?
Okay, I may start, and maybe Pierre will elaborate after that. But clearly, the first one, as I said in my presentation, is that when we started the project, the 5G was really not mature. It has progressed in France since then, since 2018. But until 2020, we didn't have networks, we didn't have chipset, so we didn't have anything at all. So, of course, we start to perform our tests with 4G, waiting for the 5G to be there. And we have been forced to make our own telematics with 5G, with buying some chipset from Simcom, making our own reference board, and also to get either test networks, external networks from Bouygues and Orange in Tecmo, and also to set up our own networks in Satori, so to have our own development. So we don't find commercial solution both at network side and at UE side at the beginning, and that's what we have been forced to make our own development. And the other thing is that we, as I say, it has been very complicated to have this working well and to reach the performance that we were expecting. And still with, for instance, with the 5G millimeter wave, we're still struggling with enhancing the parameters, 300 parameters that have to be set up in the G0B, and to have the optimal configuration, to have the good informing parameters, the good antenna position, the number of cells. And because we expect that with one cell and one device in the network close to the antenna, we should reach 500 or megabits or 1 gigabit downlink with the millimeter wave. And today we are, I would say, quite far from there. So still improving and still enhancing. So that needs important skills and important support from the network operators and network vendors. Pierre, if you have something to add to that.
Yeah, no, I agree with what you said, and also for going towards the development of our CAM service in the infrastructure and the vehicle was an important aspect for us to integrate everything all together. Was to go from this development to the all trialing needs an important integration work that was also very challenging. So yeah.
Super. Thank you both. Impressive. Also, I don't see any questions still. I'll wait. I think one just came in. This question is from Robert Johnston on the lane merging example that was mentioned in one of the presentations. Does technology currently monitor the vehicles from all traffic lanes or just the furthest most inside? Also, what are the most promising results for future testing development? Who would like to take this question?
Yeah, for the use case, it's monitoring the all traffic lanes. So the idea is that we know the road topology, and we monitor the vehicles that are driving by in all lanes to assess what are the potential conflicts and to react accordingly.
May I add that we have both the connected vehicle that provides through the CAM message their position and speed and blah, blah, blah. And we also, thanks to the roadside perception, we have the vision of the other vehicles which are not connected to have a global view of the different lanes and the different zone. Of course, on the area which has been populated with sensors of the zone of intersection. So we will not cover all the tracks with the perception. We just cover the area which presents some risk of injuries, of incidents.
Yeah, and for the second part of the question, what are the most promising results for future testing and development? So yeah,
so two things. So the latency, which is very essential for security message for V2X, from my perspective, and also the high throughput will allow exchange of raw data, and especially perception data, both from automated vehicles and infrastructure. So we can end up with a good enabling solutions with 5G for cooperative perception and cooperative driving, as it is defined in IZAD. So yes, the high reliability, but also the low latency and the high throughput are the key elements that will permit make efficient and to make possible the cooperative perception and cooperative driving.
Thank you. A second question. For such high reliability services, are you considering the URLLS LSC slice deployment during the project lifetime?
We were considering that at the beginning, but in fact, as I said, release 16 is not there. We have some private networks just starting with release 16, but commercial networks don't have release 16, so we don't have the slicing, we don't have the URLLC, so we are missing plenty of things. So tomorrow, with another project, we may have this announcement thanks to these features of 5G, but unfortunately, in the time frame of the project, we were not able to have them available.
And yeah, maybe to complete, to add another point related to this and also to the previous question, we see in a lot of projects that now like infrastructure service, but we already deployed with a MEC already, but now that will come with no new services and the possibility to for example have slicing is promising for next testing and activities that we will have, but it will be in the coming years, I hope.
All right, thank you, Pierre. Thank you, Lorraine. From what I see, we don't have any other questions coming in. So with this, I would like to thank the speakers again for the insightful presentations today and for giving us a clearer look at the 5G MOBIX trial site in France. It was a pleasure having you here. And I would also like to draw your attention to the rest of the webinars that are coming this and next week. The trial, the results and the outcomes from the German trial site on Wednesday, then from the Dutch trial site on Thursday, and next week from the South Korean trial site. So we hope to see you there as well. And yes, with this, I would like to thank you and wish you a lovely evening.